me split into two. No, let's start here. Now we will start the non-ceramic insulators. Non-ceramic insulators, as I mentioned, they are made from silicon rubber, and silicon rubber there is a fiberglass core. This is what you can see here. This has happened in one of the Gulf countries in the UAE. This is a 400 kilovolt line, and the 400 kilovolt. If you notice here, there is no line here because it's a bundle of 4 conductors. It's fall in the ground, and the reason for that because there was a crack. This is the energized end of the insulators. There is a crack here in the fiberglass core that leads to a complete mechanical failure of the insulators, and the whole thing touches the ground. So this was a huge failure here. Imagine a 400 kV line that is drops on the ground. Okay, so this is just an example when you have a failure, and you can detect this in early stage. What are the consequences of this? So for the non-ceramic insulator, we'll talk about 2 things again. We will talk about evaluating the aging condition of the insulators, and we'll talk about that. How, because as I said, rubber is susceptible to aging. So how we quantify this aging, we'll talk about it. And then detection of damages. Internal damages, we mentioned also in that one of the disadvantages of the silicon rubber insulators that internal damages, they are very hard to detect. You cannot see it because they are visible. So how we use this technique to do that. So let's start about evaluating the aging performance. The insulator surface, let me talk about, start from the beginning. The advantage of silicon rubber, we said it's hydrophobic, okay, hydrophobicity. Hydrophobic, phobic means someone scared of, hydrophobic, so, or enemy of it. So hydro means water, okay. So what does this mean? So if I have here a surface of, this is a silicon insulating, and this is ceramic, and I put water droplet here, you will have here the water droplet as discrete. Here you will have them like continuous, like this. Why? Because of the surface. This is called hydrophobic, but this is hydrophilic. So what is the advantage of this? When you have the water droplet as discrete as this, there is no continuous path on the surface for a leakage current that will lead to a flash over, as we have seen. But here, because the water is continuous almost, there is a path for the current from the high voltage to the ground, then this will lead to a flash over. Okay? Now, this is initially the status of the silicon rubber. But as the insulator ages with time, the water droplets start to change its shape. It goes from this to this, okay, until it goes to as if it is like the ceramic insulators. So you want to evaluate the surface by looking to the water droplet shape, okay? So one technique called the contact angle measurement. So you measure the contact angle between the, this is the contact angle between the water droplet and the surface and the water, okay? And if it is greater than 90, it's a good. Less than 90, it's not good. And we have it either on static or we call it dynamic. There's no need to go through this because we will not talk about this in details. But this is the practical way of doing it in the field, because this is not very practical. You have to put a droplet, measure the contact angle. This is usually done in the lab only, not in the field. But in the field, what we do, we spray the insulators. Now, once you spray the insulators, you will have the water droplets. You see here, this is HC1, class 1. Now, based on the size of the water droplet, which we want them to be small, how discrete they are, we want them to be split from each other, we classify this from HC1 to HC7. 7 when it is completely wet. So as you can see here, as you move, the water droplet becomes bigger and bigger. Now we start to have a water film, much bigger, and this. So eventually the insulator goes from HC1 to HC7. We don't like that. We want to make sure that the insulator stays in this. Otherwise, once the insulator becomes in this state, it is no different than the ceramic insulators. And we know that a flashover now will happen, and the insulator will lose because it loses its main advantage, which is the hydrophobic nature. Now, this is a manual technique. You go in the field, you spray. You have to do that when you are away from the insulators. Maybe you can have a sprayer for a longer distance, but you have to have an expert that can go and take the image and start to compare manually. So we want to automate this process. And we started this we used what we call a 3-class problem. Instead of 7 class, we said, okay, we'll have like a good, which is a class 1 or 2, medium, class 3 and 4, and bad, which is 5 and 6, maybe 7. Okay, so we have it only 3 classes, and this was a project done by an undergrad capstone project. So basically, we have a system developed, and I will show you a demo later on. So basically, there's a water pump here. You pump the water on the surface of the insulator. Then you take an image, and the image will be transferred into a computer, and the computer will tell you what is the class. It will do the classification automatically. Okay. Now this is the interface, so we need to understand what is behind this. What is the algorithm that is used based on the machine learning, of course. Has been done to reach to this level. So basically, what we have, we have images in the 3 classes. Okay, and then we change this into the grayscale, the original images, and we use something called edge detection algorithm. This is one of the famous image processing, and I will explain to you in a very simple language what is this. So basically, you come here. We did what we did. We split the image into 4 images, each image into 4, each image into 4, and then we have we try to have those small pieces, and we want to see what is the color here. Is it white or black? So we have something like this. These are the segment to 4 subset images, and then we have blocks. Okay, so each block is made from 2 pixels. Okay, so it's either white or white black or black white or black black. There is no other thing here. So we have these classes, these 4 classes, or these 4 different blocks, and we give them numbers. Okay, so we have this is 1 1. This is 1 0 0 1 and 0 0 numbers. Okay, so it's either white 1 or black is 0. Okay, so again I have the image split it into 4 images. Each one I will have those small blocks here. Each block is made from 2 pixels, so every block will have it as a number like this. Okay, and then we find what we call the gray level co-occurrence matrix. Okay, GLCM. So what's basically here? This matrix will have 4 parts. We'll have it the summation of all the 0 zeros or the black, 0 1 1 0, which is the transition from black to white or white to black, and then all the white. And then I will add. This is the summation. This is each one, the summation of all the blacks in the 4th quarter of the image. And this is the summation of all the black-white segment, or white-black and white-white. And then you look here, these are the 3 images of the, this is a sample of, so these are the 4 parts. So the insulators is made of 4 parts. Each part will have a 2 by 2 matrix. 2 by 2 matrix. Okay, so this is 4 part, this 2 by 2 matrix. Okay. Now this is the summation of, as I mentioned, the first element here, all the blacks. So you can see here as you go here, you will have more and more in the black. Why? Because it's more weighted. Okay. Now you will see this number and this number, they are very close to each other because this is the black, white, white, black. So they are close to each other. And then this number is all white colors. Okay. So there's a question here. Let me see. Can you please repeat the summation part? Okay, the summation part, let me do it in a very simple language. Let's look here. Sorry. Let's look here to this only. Okay. So here we'll have pixels, 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 pixels. Let's say I have 5 pixels or 6 pixels. So this one is, let's say this pixel was completely black, so it is 0, 0. This is 1, 0. This is 1, 1. Then this is again 1, 1. This is 0, 1. So I will count in this, the whole segment of the image, how many 0, 0 I will have. Just count them. This is called reoccurrence matrix, and I will put the number here. How many 0, 1? I will put the number here. How many 1, 0? So this is summation of the occurrence of 0, 0 or 0, 1 or 1, 0 or 1, 1. Okay? Just counting, just a counter here. So as based on this called edge detection, because it is detect between the white and the black, which is water droplet or no or wet surface. Okay, so this is the matrix, and it's clearly that the features you can see here. For example, this is very, very clear, and you can see here that in each one of those, they are, I mean, if you look here, they are very similar to each other, the components here within the 4 by 4 for each one of them. So for example, look to this here. Okay, so now when you try to draw this, you will find that they have very good cluster, very extremely nice cluster. Okay, and we got very high accuracy when doing this. So let me show you here a demo for this. Hopefully you can see this. So here, watch. Now we'll spray the water. This is a good classification. So we'll come here. We'll take capture the image. This is the image captured, and then the processing, and we'll give you HC1, which is good. Now this is a bad insulator. We will again spray the image. Okay, and then here we'll capture the image. It's bad, wetted, and we do the classification. This is called bad. Okay, now this was an initial work. Then we moved from the 3 class to the actual problem, which is a 7 class problem, and that was a work by a master's students. So we classified all from HC1 to HC7. And this is the grayscale, and we did exactly the same, the GLCM matrix. We'll do it the same thing here. And now he tried to try different combination between the features. So he tried 4 by 4. 4 by 4 meaning what? The image, he split it into 1, 2, 3, 4, 1, 2, 3, 4. So 4 by 4 image. So each one of those is a matrix, then 6 by 6, then 8 by 8, then 10 by 10, and use different classifier, linear, polynomial, second order, KNN 1 and 3. Now we understand what is KNN 1, 2, 3, and 5, then neural network, and try with the combination of the features and the classifier, what is the accuracy of that. And we achieved, I think the maximum was somehow in the high 90s, mid 90s, something like that, maybe 94. This is one of the high. We got some 96 in some other combination. So you can see here is very high accuracy that we achieved here. This is one of the confusion matrix. These are for the testing sample. You see very few cases that are misclassified most of the time the class matches the intended, and when it is completely weighted, it comes easily. There is no misclassification. The only misclassification happened when you have low, when we have the classification is good. The second point that we will try to do, or to the second problem we try to solve, is trying to detect problems inside the insulators. So like a crack in the fiberglass core. So as I said, the polymer insulator is basically the following. There is a fiberglass core here. On top of that, there is a silicone rubber on top of it. So basically, this is like a molding process. So we have the fiberglass core. We go to a two-piece mold, inject the rubber, so we will have this the insulator. I mean, it goes through, and then we have here one side is the high voltage, the other side is the ground. Let me see. There is some questions here. Let me address them before we move forward. What we do with misclassified events? Ignore them? Oh, yes, of course. I mean, for this gives you how good is your classifier. So if you use this classifier, you have a 98 certainty that you will classify the defect correctly, and 2% is you will not classify them correctly. Okay, and the point here is that you see that the misclassification, it will happen to a nearby classes from 1 to 2, which is still hydrophobic. Okay, one thing you have to make sure that your classifier doesn't do is, for example, you have a class 1 and you misclassify to 7 or 6. That's extremely bad. So you see that most of the time the classification is in the class beside it, which is expected. Okay, so what are the problems? Okay, for example, if there is a crack, okay, another question, let me answer. Would it be safety hazard if you misclassify and you still no, there is no safety issue here. You want to classify the insulator. So if misclassify, if this HC1 and this is HC2, there is no big deal. It's still hydrophobic. It's not the exact class, but it's a close class. So that's good enough for you. But there is no safety hazard here. This is just you are trying to classify the insulator. If it is 5 and 6 and 7, this is bad. All of them, they are bad. So this is like one cluster, which is a bad cluster. So that's and you can see the classifier does not combine extremely bad classes with those ones. Okay, so if there's a crack in the fiberglass core, when it is small, it might be very hard to detect it at the factory, and this may manifest itself because of the mechanical load, start to progress until you have complete failure. And we'll talk about the techniques that are used to detect these defects. Or because, as I said, this is done in a two-piece of mold injection. So when you do the injection, maybe there is some metallic particles that the mold is not 100% clean. If there is like very small, tiny metallic there inside here, so this one also can lead to some internal partial discharge and complete failure in the future. Or bonding, because the rubber has to bond perfectly or extremely good to the fiberglass. So if there is air voids here, these air voids, they will initiate partial discharge, and eventually this will lead to the failure. So these three defects, we want to detect them in the factory, try to see if we can detect them. Now the techniques, there is an IEEE task force. They try to use different techniques to detect those defects using the resistance measurement, partial discharge, radio influence voltage, leakage current, etc. They don't found any technique that is capable of detecting all faults. Some techniques can detect some faults, others can detect other faults, but there is no technique that can detect all the faults. So what we are trying to do here, we are trying to do a different way of inspection using the very high frequency called near field sensor. In the near field, what we have here, we have a waveguide, and this waveguide will send very high frequency, and it will be reflected back. And this will be taken and it will be rectified, and we'll get a DC, sort of a DC voltage. Now, based on the dielectric constant inside the fiberglass, you will detect different signal. So for example, you have here 3 different types material. You will have an insulation. Insulation means you will have rubber and you will have fiberglass. This if it's healthy. And the dielectric constant here, we are talking about 3 to 5. Then if you have air, void, or crack, this is 1. If you have metallic, this is very high, thousands. Okay, so based on the dielectric constant, the amount of reflected wave will be different. So this is the principle that we use to detect. Now, this is a video. Hopefully, you can hear the voice. If not, please let me know. If you can't hear the voice, I can talk myself. Can you hear the voice? Please tell me yes or no. No, okay, so I will talk. Okay, I will explain. So here, basically, you will have the insulator rotates. This is rotated. There is here the sensor. It transmit and receive the signals. It goes CC, goes to an amplifier, and then data acquisition, and then it shows here on the screen. Okay, so when you do it in the screen here, you'll see that when there is no defect, it's like this. If a defect, you have a spike like this. Okay, so this is the whole idea. So we found that, and this is a group again of undergrad students, if there is no defect, we have something like this, smooth transition. And this smooth transition, because when you take a cross-sectional area of the insulator, we found that the rubber is not uniform. Okay, so in certain areas you have more rubber than others. This is why we have this transition between the, in the reflected signal. Okay, now, but when there is a metallic, or if there is an air void, then you will see spikes like this, very severe spikes, and those spikes are distinctive, meaning that each one has certain features. So a work was given to a master's students. He's trying to apply machine learning and neural network, start to take some frequency components from those, and found that we can detect like with 95% accuracy using those classifiers. Now, we can do another interesting thing, which is a 3D image we can do for the insulator. And here we have a metallic enclosure. You can see a very sharp increase. If there is a crack, you can see here, this is a crack. So they have multiple air voids, sorry, multiple peaks. And if there's an air void, there is one peak here. So even if we do it's like a CT scan or like an imaging system, we can detect. This is enough about outdoor insulators. And let's move to the second part, which is the transformers. This is a transformer that this was in Abu Dhabi. This transformer was on fire for 2 days. It was a fault inside, and for some reason, the people who came to fix the problem, they spray water of it, which is stupid from them, because when you have a fire in oil, this is oil, this is inside oil, and if you add water to it, it makes it even worse. So this stays until the whole thing. This was a 500 MVA transformer. So transformers are extremely important components, and they are expecting to live for like 40 years. Okay, and it is the most expensive asset in the network. percent of the cost of the asset is transformers. And especially the big ones, they service huge areas. And their installation age with time, like any installation system. Now, their installation system is oil and paper, and both age with time to leading to a flash over. Now, the main thing that we'll talk about today is what we call the partial discharge. From its name, it's not a complete discharge, just a partial discharge means it is a localized discharge. There is an interesting question here. Let me answer it. It says, transformers are more expensive than generators. No, they are not. However, in any network, you have only one generator in one circuit, but you have many transformers. So the cumulative cost of the transformer is more than the generator. But as a single unit, of course, the generator is more expensive to the most expensive transformer. But because the number of transformers we use in any circuit is very large, because we have to step up the voltage and then step down the voltage in different stages. So the total cost of the transformer is more than the generator. Okay, so the PD inside the transformer, the partial discharge inside the transformer can be externally, like coming from a sharp point or a surface discharge, or internally, a void in the paper installation. So in the transformer winding, you could have it external to the winding or internal to the winding inside. So let's have here, this is, for example, when you have a sharp point. When you have a sharp point like this one, if you see the core here, the core has a sharp point, and those sharp points are close to the installation, so these start an arcing process here, partial discharge. And this start will damage the insulation here in the conductor, and this can lead, if not detected at an early stage, so this is a sharp point to the insulation, can damage the whole thing. Also, we have surface discharge on the insulators, so it happens on the surface of the insulator that can lead to a complete failure of the insulation. A void, if you have an internal void in the insulation, it will start to propagate like this until you have a complete failure in the insulators. So these, regardless of the type of the fault, they can propagate, and they can lead to a very catastrophic failure, as you can see here in the transformer. The transformers, their main major problem is that they are a tank of an oil. If the oil explodes, it's a huge thing. It's a huge disaster. It's also a safety hazard. Now, how to detect the partial discharge? Partial discharge, when it happens, remember, we have an insulation. Inside, there is certain defect, and there is an arc here. When an arc happens, there is mechanical energy transferred. There is electrical signal transferred. There is an electromagnetic waves transferred. There is a thermal effect. There is a chemical energy because of the fault happens here. They start to have a chemical changes. There is an optical because what is happening inside, there is an arc, so there is an optical. So see here we have different phenomena that comes with the partial discharge. Now, based on the insulation system we use different sensors. But in transformers, the most used sensor to detect partial discharge are either through dissolved gas analysis. As I mentioned, whenever there is an arc, there is chemical changes that happen in the oil. So we do what we call dissolved gas analysis. And from the dissolved gas analysis, we can detect different types of faults. I will not talk about this today. Then we have the ultra-high frequency sensor, which is an antenna. And this antenna, we can insert it. We have to insert it inside the transformer. And if it is not pre-designed, pre-installed when the transformer is new, then usually I have only one access point, which is from the drain valve. So I will insert it there. Okay. Why we cannot have the antenna outside? Because the transformer is a grounded body, so it is act as a shield. So if there is an arc inside or a partial discharge, I cannot detect it using the antenna. Finally, we have the acoustic emission sensors, which is made from what we call piezoelectric material. The piezoelectric material are used to change mechanical vibration into an electrical signal. Okay, we'll talk about that a little bit more details. So I will be using these two sensors as we will see here. This is detailed comparison between them. Okay, so what is important for us, of course, DG, I will not talk about the DGA, so I will talk about the frequency. So this is the frequency for the ultra high frequency or the antenna. This is the range for the AE or the ultrasonic sound. So you can expect that that the system here is much cheaper than this system or the ultra high frequency system. Okay, here I'm measuring sound, here is measuring electromagnetic wave. Now, the detection sensitivity on the antenna is much better than the ultrasonic because the ultrasonic signal attenuate in a faster rate inside, especially if it is happening inside the installation, it attenuates, it dies off very fast, and sometimes it's hard to detect using the acoustic sensor. However, the RF antenna is much better. However, the problem of the ultrasonic of the RF antenna, you have to insert it inside. So it's a sort of intrusive, little bit intrusive, means it has to go inside. However, the AE sensor, using a magnet, you just attach it to the tank of the transformer. So this piezoelectric material will be attached to the tank, and whenever there's a partial discharge, there's a little vibration at the ultrasonic range, then these sensors are sensitive to detect this very tiny vibration that happens in the tank. So this is an important. I can have multiple of those sensors, and this can very important to localize the partial discharge. Now the antenna, it's very hard to have multiple of them, as I mentioned, unless you pre-install them before you energize the transformer. So what I'm gonna share with you here, we'll talk about some PD detection using RF antenna and acoustic sensor. So we'll start with the RF antenna at the beginning. So we have in the lab, this is a tank, and the tank has certain openings here. So I can insert the electrode through a bushing inside. The tank is filled with oil, okay? And I will have an antenna inside. This antenna is connected through an amplifier. And this amplifier is fed by a DC source to give the power, needed power for the amplifier. And then I will have an oscilloscope or computer-driven monitor to check the signal. Now, these are some of the antennas. Now antennas that we want to do, we want to insert them inside. So we use what we call fractal antenna. These antennas are made on PCB. In a board, okay, so they are very small actually. The size is very few centimeters, so they can easily be inserted in those holes, okay. And in case of the transformer, if it has a drain valve, we can easily insert them, and they come up in this interesting artistic shapes, and they are like this. So we did studies using the different types of antennas. So this is the fractal antennas. A fractal means you see this shape, it repeats itself. Okay, so it repeats itself. In different ways. So this is we call a fractal antenna. Now, why we want to do this? Okay, there is something here interesting to understand about the antenna. Now, the smaller the antenna size is, means the length of the antenna, the higher the frequency it can detect. So if you have a small antenna in this size, you can detect something, let's say, in the 60 gigahertz. What's wrong with that? What's wrong with that is that I need to measure this. An oscilloscope to measure 60 gigahertz is very, very, very expensive. I cannot do that. So I need to have a very long antenna to have this in the, say, 1 to 3 gigahertz. But a very long antenna, I cannot insert it inside the transformer. So this is basically the compromise I have. So this is one wire, by the way, but it has different shapes. So it has this all different shapes. So it can be a very long antenna, but it is confined in a small space. So this is the whole idea. This is the frequency. Those who study antenna, they understand this. When you have the reflection coefficients in low in dB, mean that these are the points it has a good detection. So these are the points with a good detection. If you don't understand that, that's okay. This is not an antenna course. Now we try to detect corona, PD, surface PD, and sharp PD. So we have different types, and we notice that each antenna when detect, it maintains certain shape, which tells us that, so this signal is different than this, and this is different than this, okay, similar somehow to this. So this tells us that I can use machine learning. Once the signals are different, then I can use machine learning to distinguish between them, and we found that we have extremely high recognition rate to tell the difference using each type of the antenna, which is something very, very good. We did a similar study. We increased the number of defects. We added a void inside here, and we used the ultrasonic sensor or the acoustic sensor. You can see here, this is the acoustic sensor here. This is a magnet, and this is the sensor. This is the sensor, and this is the magnet. So this is a piezoelectric. You just attach it to the surface, which make it very interesting, meaning that it is easy to do. It's not intrusive. We tried here to do different things. We try to insert a barrier between the sensor and the source of partial discharge. So when we have a barrier, because this is happening in reality, that you don't have a line of sight between the source in many cases and the sensor, there are some objects. So the PD here, it has to go through this. How this will affect our classifiers. Also, the transformer temperature is not constant. It changes, depends on the load. So what will happen if I change the oil temperature? Will my classifier be working still or not? Another thing here, what if I have the partial discharge at different locations? Let's say location 3 or 4 or 9, close or far away, how my classifier will work. So this is an acoustic signal that we detect. This is, we use different features. This is the Fourier transform, wavelet, and we use the BCA here as a classifier, as a feature extraction as well. And here we use different classifier, polynomial, quadratic, SVM, and KNN. And here's some of the results. So here, this is the basic thing that we did. We have different classifiers, different features. So we reach up to 94% using the BCA and the KNN. Okay. Now, if you we try to see, okay, what is the impact of the following? This is the partial discharge, how it would look like. This is the sensor. If I generate it at location 4, and this is how it looks if it is generated at location 9. So the question is, what if I train my classifier at location 4 and test it at location 9, so that all the data I have here we use for training, all the data I have here I use for testing. So the classifier never see anything trained at this location. And when you look here, you see that the classification went very low. In the original case, we have in the 90-80 range. Here it is in very 64, 65. This is the best we can get, which is something bad. So what we did here, we mixed them. We mixed location 4 and 9 together, and then this we went back to the 90, close to 90 range. So this tells us that the classifier has to be well trained at different position, which will limit the practicality of using this. We try to see the impact of temperature. So we train at room temperature and test at PD collected at a higher temperature. And again, as you can see here, the classifier did very poorly. Then we train and classify at both combination of the two, and then it improves. One of the things that we are trying to do is trying to generalize the classifier. We found that this is not good, because I cannot test the classifier for an endless number of scenarios. So we want to have features that are less sensitive to the changes. And recently we are working on a paper that help us. We use some very complicated mathematical tool there. There is no time to talk about this, and we just submit this paper. But we managed to achieve high accuracy, although the system was trained at completely different conditions. That takes us to the end of my lecture today. And before I end, I'd like to just highlight, where is this condition monitoring going? What are the new trends? The first one is the use of drones. Now, the data that I told you about that we collect for outdoor installators, okay, people, they have to use a helicopter to go and do the inspection. It's needless to say that this is dangerous, not safe. And plus, the efficiency is extremely low to do the inspection. Now, utilities, they start to use a drone, but these drones are manually operated, meaning that you are staying beneath the tower. You have your drone there, you manually control it. You have a camera, basically. This is the only sensor used so far by the industry. And you try to collect images, and you feed images continuously, and in real time you can see if there's a defect. But this is only, you can see the pictures or the photos of the insulators and the hardware. But if there is internal defects, you cannot see. So you have to add more sensors, and obviously this is going on. The future trend now to have autonomous drones, actually, meaning drones that you give them the GPS coordinate of the tower, and they do that autonomously. And I will show you a small clip of a video of a project that we did, just to show the concept, how it will look like. Another thing which is not related to drones, or could be related to drones, which is application of deep learning. Deep learning is a new concept that people are starting to use nowadays, especially with images. It's different than machine learning. In machine learning, if you learn something today, you see that this is a tedious process. You have to collect a lot of data. You have to select features from this data. In advance, we don't know which is the good features, which is the bad features. So it's a trial and error process. And then I have to reduce the features, remove some of the redundancy. So it is a very, very tedious process. In deep learning, no. You feed the pictures to the classifier, and the classifier itself, it selects the most important features, and one of the most important technique called the CNN, convolutional neural network. So it's basically a neural network, but instead of having 2 hidden layers, it has many hidden layers. So you have to have a huge number of images to be able to train. Otherwise, you will have something we call it overfitting, meaning that you will have a good model for your data only. If you have different data, then it becomes extremely bad. So CNN is related to big data, yes, as your colleague is asking. It is, but you have to collect huge data to be able to train it. Now, big data is something, I mean, you can look to deep learning from that perspective, but big data, when you have a huge data, maintenance records, etc., and I want to extract information from this big data. Okay, so it's a little bit different than CNN. CNN, you have the data, and you use it to train your network, and then you try to have your classifier working. Just to give you an idea, the 7-class problem that we did, I gave it to a master's student. It took him, I think, around 9 months to finish the work using machine learning. you have seen a combination between different features and different classifiers. I gave exactly the same data set to an undergrad student, co-op student, who worked for around 3 months or 2 months effectively, and he got exactly the same result using deep learning. So we get the same accuracy, but with a much easier way. Much easier system. And the disadvantage of the need for a huge data can be resolved. There are certain ideas. I don't need to go in details here, but there's something called ready networks that are pre-trained on different images. You need just to change the last layer to your specific target. You can also take the images, rotate them, change the lighting conditions, so you can generate a lot of data points there. So there are tricks also in the deep learning. Let me show you this video. So this is again a graduation project. Here, students, this is a drone. So here manually, he will just launch the drone, and then he will raise his hand. He will stop. He will not do anything now. He will not, the drone now autonomously will go. And here you see the images that is transmitted by the drone. The inserters are hooked up here in this tower. When it reaches, it will start to send the images of these insulators, and then start to do the classification real time. It says polluted or not polluted. So this is give you the percentage, how much is the insulator is polluted. 99%, so it is highly polluted insulator. Then after that, the drone is going back to the origin. Again, everything is done autonomously. It will come here and it will drop itself without the interference of the operator. The operator is not really working, and it sends here the GPS coordinate if there is insulator that is really bad, and it comes here. So this is like a very primitive work for this, but this is where the trend is going. Finally, for the transformers, also there are other things. For example, application of Internet of Things for PD monitoring, meaning what? You have your sensors. You said this data will be sent to a cloud where you have all the signals continuously there, and you try to apply your machine learning in real time. Another direction is to use sensor fusion, meaning, okay, acoustic sensors sometimes give you false information. RF antenna gives you also sometimes false information. What if we use both of them? And this is a small study we did here. We have 3 acoustic sensors, okay, and we have 1 RF antenna, and we use the RF antenna to trigger the other sensors. So if the RF antenna detects something, it will trigger the measurement. So if both the RF antenna and the acoustic sensors are measuring something, so this is most likely is a partial discharge and nothing else. So in conclusion, condition monitoring and diagnostic of insulation is crucial to the integrity of the power system. It's very, very important to do that. Machine learning can be applied and start to be applied nowadays to detect or to improve the ability of detecting defaults in the insulators. Most of the work is done in research-based lab. Now, it's the time to move from a research labs into commercial applications in the field, and this is another area where machine learning now is start to be implemented. With this, please let me know if you have any question. I will stop sharing now. If we need to go to sharing, I will go back here, but let's see if you have any questions. If you want to ask a question, you can ask. I can actually I can unmute you if you want to say anything. If you want to say anything, I think. Let me see if you are. Okay, let me take this mute on entry, so you can unmute yourself if you want. Everyone now you can unmute or mute yourself if you have any question. I will stop the recording